Welcome back to CS111. In this lecture, we're going to take a look at a new type of data structure known as a deque. We're going to work with a linked implementation of a deque, and as part of that, we're also going to explore how we can use doubly linked nodes in some of our data structures. The name deque refers to a double-ended queue. Basically, we can go and add items from the front and rear of the queue, and we can also go and remove items from the front and rear of the queue. It's not a case where we're tied to going and just adding at the rear and removing from the front like we are with a traditional queue. The ability to go and add and remove at both ends of the deque allows us to use it as a replacement for a traditional queue, and we can also use it to replace a stack. It just basically depends on what end we go and add or remove things on with what version of those other data structures it's going to behave like. One note that I want to mention here is that the ability to go and substitute out deques for these other data structures is such that Java itself actually suggests using its built-in deque class if you're trying to create a stack rather than the built-in stack class, because the way the internal implementation of the deque is, it actually performs better than the stack in a lot of cases. Now that's something that's specific to Java's built-in data structure types. It's going to depend on how you go and implement them as in your own case as to which is better, but it just goes to show you can substitute a deque for either a stack or also a traditional queue. So that you can see how a deque compares to stacks and queues, I put together this diagram that shows the different ends and the different operations that are supported on those ends when we go and try to add and remove things. You can see here on the top line for each of these diagrams that deques support going and adding and removing both at the front and the rear. When we have a stack, we're going to go and push and pop at the front, which we're also saying is our top. When we have a queue, we go and enqueue items or go and add them to the queue at the rear, and we go and remove them by dequeuing from the front. Deques are going to share a lot of the same operations as traditional stacks and queues, but there are going to be some differences because there's more places we can go and add and remove things from. Let's go ahead and design an interface to represent the deque, and as we've been doing with our other interfaces, we're going to give it a generic type parameter so that we can specify a particular type of item that we want to store in the deque. Let's go ahead and figure out the methods that we're going to need to support for our deque. Obviously, we'll have to have a way to create the deque, and as with our other data structures, the constructor is going to handle this. We'll need a way to go and add things to the deque, and since we're going to support adding at either end, we're going to actually provide two separate methods for this, an add to front and add to rear. Alternatively, we could design this so that there was a single add method and that it had a parameter specifying what side you wanted to go and add on, but I think in this case here going through and just having a separate method altogether is going to be a little bit simpler. We'll also need a way to go and remove things, and since we support adding and removing at both ends, removing is going to need a pair of methods as well. These methods are going to go and throw a no such element exception if there's nothing left in the deque. We're going to include a pair of peek methods that will allow us to see what's on the front and rear ends of our deque without going and actually removing those items. These will also throw no such element exception in the case of an empty deque. We'll have an isEmpty method so that we can figure out if there's anything in the deque, and a size method that will tell us specifically how many items we're storing in the deque. We'll also go and include a toArray method that will return an object array with the contents of the deque. Let's go ahead into Eclipse and code this up. Here in Eclipse, I've created a new Java project for us to use with our interface. Inside the source folder, I'm going to right click and go to new and make a new package. And I'm going to call this edu.wvu.cs111.deq.adt based off the naming convention we've been using so far. And I'll tell it finish. And then I'm going to make a new interface inside of that package. And I'll call it Deque interface. And I'll click finish here to go ahead and have Eclipse make that file. Let's go ahead and add our tgeneric parameter, and then I'll provide some Javadoc for the interface. And then we can go and list our different methods. We're going to have a pair of methods that will return void to go and add things. First one will be add to front, and it'll take a parameter called item of type t. We'll also have an add to rear. We'll have a Boolean method that's going to tell us if our deck is empty. We'll have a pair of methods that will return t to go and peek at the front and rear. These ones don't take any parameters. We'll also have a pair of methods that return type t to go and remove from the front and rear. We'll have our size method that returns an int, and our toArray method that returns an array of objects. And I'll provide some Javadoc for these methods. And that goes and finishes up our interface. Now that we have our interface implemented, let's start to think about how we might actually create a concrete implementation of that interface. We're going to be taking a look in this lecture at making a linked version. And for this, we're going to need to have some nodes. So far this semester, we've looked at what are known as singly linked nodes. These nodes have a link to the next node in our chain. Because there's only one link, we can only go one direction in that chain. So we can go forwards, but we can't easily come backwards. And that leads to some creative ways that we might have to go and code our different data structure implementations, because sometimes we need to be able to go and do something based off of the value that's essentially ends up before us. This is why we have to go through and do things like a lot of times go and look when we're inserting into a sorted priority queue, for example. We have to go and look ahead at the next node to see its value compared to what we're trying to insert, because if I go and jump forward to that next node, I can't come backwards to insert something. Another approach that you'll sometimes see used is that you'll have kind of a trailing variable that you might drag along as you go and iterate through a chain of nodes, so that you're going to be looking at the current node with your current node variable, and then you'll have like a previous node variable that'll take a look at the last node before it, and then you'll just kind of advance both of those forward. That way, if you need to make a change before the current node, you've got a way to do that. Working with singly linked nodes like that can be kind of cumbersome, and it really does not provide us with a good solution where we want to be able to add or remove things on either end of our data structure like we do with a deck. If we just have a singly linked node, I'm going to have to start at one end, and then I have to go and advance all the way to the other end to go and add something or remove something at that end. If I have nodes, though, that are what's known as doubly linked, where they have a link to the previous node in the chain and to the next node in the chain, I gain the ability to go forwards and backwards. This is going to make it a lot easier for me if I need to go and do operations at both the front and the rear of my data structure. And it can also sometimes make things easier if I'm trying to go and make changes in the middle of my data structure's chain. In working with our deck, since we have the ability to go and add and remove at both the front end and the rear end of the deck, it's going to be easiest for us if we have nodes that will allow us to go forwards and backwards, or in other words, doubly linked nodes. We're going to go ahead and make a doubly linked node class for us to use. It's going to look very similar to the singly linked node class that we've previously created, but we're going to have doubly linked node stand on its own rather than inherit from singly linked node. And that is because we designed singly linked node to go and implement method chaining, where our different setter methods go and return an instance of the class, in fact the same instance, rather than being void methods. Going through and having that functionality makes it a little bit tricky to go and inherit things, and specifically with those methods, because the types aren't necessarily going to line up with quite what we're looking. We're going to go ahead and just follow the model of singly linked node, but our doubly linked node will be a separate class rather than one that goes and inherits from singly linked. Let's go and code things up inside of Eclipse. Here in Eclipse, I'm going to import the starter code for this lecture, which will contain our singly linked node class. I've already downloaded the starter code from eCampus and saved it to my desktop. To go and import it, I'm going to go to the File menu in Eclipse, and I'll go to Import. Under General, I want to bring existing projects into Workspace, so I'll click Next. The data right now is stored inside of a zip file, which is a type of archive. So I'm going to click the radio button here for Select Archive File, and then I'll go and browse for the file on my desktop. And it's this starter code zip file here. Inside, I've got this nodes project, and the box is checked for it, so it's going to import it. So I'll go ahead and click Finish. And that's going to go and bring in my existing nodes project. This has right now just our singly linked node class in it, and that's inside this edu.wvu.cs111.nodes package. We're going to go ahead and create our doubly linked node class inside of this same package. I'm going to right click on the nodes package and do a new class, and I'm going to call this doubly linked node. And since we are not going to be inheriting from singly linked node, I'll just leave superclass the same as java.lang.object. And I'm going to click Finish. A lot of what we're going to set up here is going to look the same as what we did with our singly linked node class. So for example, I want to give it the tgeneric type so I can specify what type of data I'm going to be storing in the node. I'll also go and provide some java. My class is going to have 3 fields in it. It'll have a protected field that's going to be of type T to store my data. It'll have a protected field that's going to be of type doubly linked node with that generic parameter T, and this one's going to be called my previous node. And I'll have another protected field that's going to be of type doubly linked node with the tgeneric that I'm going to call next node. This way I can store my data for the current node, and then I can go back to the previous node in the chain and forward to the next node in the chain. And I'm going to provide javadoc for each of these fields. Just as we did with the singly linked node class, we're going to provide getter and setter methods for our 3 different fields. So, for example, my getter method for data is going to be a public access modifier. It's going to return a value of type T. It'll be called getData. And we're just going to have one line of code in here, and it's going to return the value this.data. I'll also go and provide a setter for data. This one's going to be a public method. I'm going to use method chaining with my doubly linked node implementation, just like I did with the singly linked one. So my return type here is not going to be void. Instead, it's going to be doubly linked node with the T generic parameter, because we're actually going to return this same instance that we're going and calling this method on. This method is going to be called setData, and it'll take a value of type T that we'll call data, and then we're going to store that data argument inside of the data field. And for the method chaining to work, we're going to return this. we'll do the same thing with our other fields here. So we'll go and do our get and set previous. So I've got public here. This one's going to be return a type doubly linked node with the T generic, and we're going to call this one get previous node. Doesn't take any parameters, and it goes and returns this dot previous node. For its setter, it's going to be public. It'll return a doubly linked node with the T generic, and it's going to be called set previous node, and then its parameter will be of type doubly linked node with the T generic, and we'll name it previous node. Here we're going to go and say this dot previous node equals previous node so that we can go and store the argument, and then we'll return this. We'll also go and handle our next node field. So we'll have a public method that's going to return a doubly linked node with the T generic called get next node, and then its body just going to be returned this dot next node, and then we'll have the setter. It's going to be public, return doubly linked node with the T generic, and it'll be called set next node, and then it'll have a single parameter of type doubly linked node with that T generic that we're going to call next node, and then our body will be this dot next node equals the next node parameter, and we'll return this. And I want to make sure that I provide JavaDoc for each of these methods. Now that we have those getters and setters created, let's go and work on our constructor methods. And we're going to provide two of them for this class. The first one is going to take values for all three of our fields. So this is going to be a public method we call doubly linked node, and we're going to have our three parameters, and I'm just going to list them in order as T, and we'll call this one data. We'll have a doubly linked node of type T, that's going to be our previous node, and then we'll have a doubly linked node of type T that'll be our next node. And inside the body of this constructor, we're just going to go and store the values, and I'll use the setters for this. So I'm going to say this dot set data, and I'm going to store data, and then I'm just going to go and align the dots here for the other setters that we're going and chaining together. So I'm going to say set previous node to previous node, and we'll set next node to next node. And we'll give this constructor some JavaDoc. We're going to create a new doubly linked node. Param data is the data to store in node. Previous node is the link to the previous node. And next node is our link to the next node. We're also going to have a version of the constructor that'll just take a single parameter with the data that we're trying to store. This one will go and set both previous node and next node to null. So this will be a public method. It'll be called doubly linked node, and we're just going to have that single parameter of type T. Inside the body here, what we're going to do is we're just going to rely on a call to the main constructor, the other version. And for that, we're going to go and say this, and then I'm going to provide values for the three parameters that the other constructor takes. So the value for data will be whatever we get as data when this one is called. For previous node and next node, those are both just going to be null. And we'll provide some JavaDoc for this as well. I've scrolled down to the bottom of the code, and I'm going to create two new helper methods here. The first one we already saw was singly linked node. This one's going to be isLastNode, and this will tell us if there is nothing in the chain afterwards. So this is going to be a public method. It'll be a Boolean return type, and we're going to call it isLastNode, and it's just going to go and return the result from the expression this.nextNode equal to null. So if next node is set to null, that's going to signify that this is the last node in our chain. So this returns if this is the last node in a chain. And we're going to return true if there is no next node. We'll also go and have a counterpart for the beginning of our chain. So this is going to be a public method. It'll return Boolean, and we're going to call it isFirstNode. And for this one, we're going to return the result of evaluating the expression this.previousNode is equal to null. So if there is no previous node, then we're going to say that we're the first node. And that goes and finishes up our doubly linked node class. Now that we have our doubly linked node class created, let's see how we can put it to use to go and implement a linked version of a deck. In our linked deck class, we're going to have 3 fields. One to keep track of the size of our deck, and then we'll have a link to the front node in our chain, and one to the rear node. Having these direct links to the front and rear of the deck will make it easy when we need to go and add and remove items. Let's go ahead into Eclipse and see how we can code up our implementation. Here in Eclipse, I created a new linked deck project, and I went and adjusted the Java build path for that project to go and add deck interface and nodes so that we can go and reference the code from those projects. Let's go ahead and make a new package for our linked deck implementation. I'm going to right click on the source folder, go to new package, and I'll call this edu.wvu.cs111.linkdeck, and I'll click finish. Inside this new package, I'm going to make a linked deck class. So I'll right click on the package, go to new class, and I'm going to call this linked deck. Here under interfaces, I want to click add, and I'm just going to start searching for deck interface. We can see that it went and grabbed it here from my deck ADT package, and I'm going to click finish. I want to go and modify my linked deck class to add that tGeneric parameter. I'll go ahead and hover over linked deck and use the quick fix to have Eclipse add the unimplemented methods. And then I'll go and provide some Java doc for my new class. So I'm going to say this is a linked implementation of a deck, and then I'll go and list my author name. And the tGeneric is going to be the type of data to store. Before we get to the methods for our class, let's go and deal with the fields. I'm going to create a protected field that'll be of type doubly linked node with the tGeneric parameter here that I'm going to call front node. And I need to make sure that I go and import that class, so I'll use the quick fix here in Eclipse to go ahead and do that. I'll have another protected doubly linked node with the tGeneric that I'm going to call rear node. And then I'll have a protected int to keep track of the size of my deck. And I'm going to provide some Java doc for these fields. When we go and create a new instance of a linked deck, like with our constructor, there's 2 major things that we're going to have to do. First, we want to make sure that our links to the front node and the rear node are both set to null, which should actually be the default value since this is a reference type. Having both of these set to null is going to reflect that we have an empty deck. We'll also want to make sure that the size field has been set to 0 since there's not currently going to be anything stored in the deck. This is actually the default value for a primitive int, but we'll go ahead and make sure that we have a constructor that goes and sets it explicitly, just for clarity's sake. I'm going to go ahead and create my single constructor right after my fields. It's going to be a public method, and it'll be called linkDeck. Won't take any parameters. So what I'm going to do here is I'll first go and set the front and rear nodes to null to reflect that we have an empty deck. So I'm going to say this.front node equals null and this.rear node equals null. And then we're going to go and set our size to also indicate an empty deck. So we'll do this dot size equals 0, and we'll add some Java doc for the constructor here. So this is a constructor for a new deck of linked nodes. Probably the first thing that we'll want to do with our new deck is to go and add something. We're looking at 3 different scenarios of how we might go and add things depending on if there's anything in the deck yet and if we're trying to add at the front or the rear. Let's take a look first at the case where the deck is empty. Here, I'm going to go ahead and create a new node, and this is going to happen whether I actually call add to front or add to rear. Once I've got my new node and I've gone and stored the value 55 in it, I'm going to update both the front and rear node fields to go and point at that new node. If there's only one item in the deck, it's both the front and the rear simultaneously. Once I've gone and updated front node and rear node to point at my new node, I can go and increment my size to reflect that I now have one thing inside of the deck. Things get a bit more complicated when there are already items stored in our deck and we want to go and add something. Let's take a look first at a scenario where we have 2 things that are stored in our deck and we want to go and add a new value at the front. Here we're going to start off just as we did before by going and creating our new node. Once we've got that new node, we need to go and hook it into our chain of existing nodes. We're going to start off by going and setting the next field in our new node so that it points at the existing front node. So that'll allow us to go forward from our new node into the rest of the chain. We're also then going to go and set the previous node in the existing front so that we can go backwards from what will end up being the second item in our chain. At this point, 33 is our new node and squarely hooked into our chain. The one thing that we've got to go do and finish up with, at least updating pointers for our chain, is to go and set the front node field so that it goes and points at our new node instead of the existing front one. That way our new one truly becomes the front of the chain. Once we've done that, we'll go ahead and increment our size counter to reflect that we now have an additional thing inside of our deck. Going and adding on to the rear of a deck that already has contents is more or less the mirror image of what we did when we were going and adding on to the front. We're going to start off by going and creating a new node, and in this example on the screen here, it's got the value 92. Once we have that new node made, we're going to update its previous node field to go and point at the existing rear node. So we're going to go through and update, in both cases, the link coming off of our new node first. Once we've done that, we can go to our existing rear node and update its next link to point at the new node. So we've now attached our new node onto the end of the existing chain. With that in place, we can go and update the rear node field so that it goes and points at that new node we've got, and then we can go and increment our size. Let's go ahead into Eclipse and see how we're actually going to code up our add to front and add to rear methods. Before I go and code my add methods, I'm actually going to go and handle the isEmpty method because we'll make use of isEmpty inside of the code that we're going to write for add to front and add to rear. So for isEmpty, we're going to return the result of evaluating the expression this.size equals 0. One thing that I want to mention is that our code for add to front and add to rear with both of those methods will be able to handle the case where the new item that we're adding is the very first thing in our deck. We don't need to have a separate method to handle the case where the deck is empty at the beginning. Let's go ahead and take a look at add to front first. And what we're going to start off with inside of the method is we're going to go ahead and create our new node. And we're going to set its next node pointer. So I'm going to say var new node is equal to what I get from calling the constructor for a doubly linked node with that t generic. And I'm going to go and call the version of the constructor that has just a single parameter, where I go and specify the item I'm trying to store. Once I get my new object back from that, I'm going to go and call the setNextNode method on it. And I'm going to set my next node to be the existing front. So I'm going to do this dot front node. So this is going to go create my new node and then have it so that you can go from the new node to the existing front of the chain. Once we've done that, we need to figure out if there's other stuff in the deck so that we can update our links appropriately. This is where we're going to use our isEmpty method. So I'm going to say if this dot is empty, which means that right now there's nothing in the deck, and this is going to end up being the only node in the deck at this time. We're going to go ahead and make it be our new rear node. So I'm going to say this dot rear node equals new node. I'll have an else clause that's going to handle where there already is something in the deck, and I'm going to update the previous node field in the existing front so that we can go backwards from it to the new node that will become the new front. So I'm going to say this dot front node dot set previous node, and I'm going to set it to my new node. So this will finish tying the new node into that chain of nodes. Will be able to go forwards and backwards from any of the nodes inside of the chain. Regardless of how many nodes are in the deck right now, our new node is going to become the front. We'll go and handle setting this once we get out of the else block. So I'm going to go and update the front node to point at my new node. So here I'm going to say this dot front node equals new node. That'll work for any case where we're going and trying to add to the front, since it's going to be the front. We'll also want to make sure that we go and increment the size. So I'm going to say this dot size plus plus. And that'll go and finish up our add to front method. The add to rear method is going to look pretty much like add to front, just the difference being here that we're going to swap front and rear and previous and next. We'll start off by going and creating our new node, and we're going to set the previous node pointer when we do that. So I'm going to say here var new node equals new doubly linked node with the t generic, and I'm just going to use the version that has the single parameter of item, and then off that I'm going to call set previous node, and I'm going to set it to this dot rear node. So this one's going to come after the existing rear node. Now I could have also here and with add to front called the version of the constructor that had 3 parameters and then just set the one that I wasn't trying to have be pointing at anything to null. But I think here going and calling the single version and then going through and doing set next node or set previous node as appropriate makes it a little bit more clear about what I'm doing. Once I've gone and made my new node, I'm going to go and figure out if there's anything already in the deck. That way I can go and update my links as needed to tie everything in. So I'm going to say if this dot is empty, which means there's nothing in the deck right now, then this is going to become the front of my deck. So I'm going to say this dot front node equals new node. I'll have an else clause to handle where there already are things stored in the deck. And for this, I'm going to go and update the existing rear node so that the new node will come after it. So I'm going to say this dot rear node dot set next node, and I'm going to set it to my new node. Whether or not there were already things in the deck, I still need to go and make my new node be the rear node, since I'm going and adding at the rear. So I'm going to say this dot rear node equals my new node, and then I'll go ahead and increment my size field. So we'll do this dot size plus plus. Next, let's go and take a look at our peek methods. So these are going to return the value that's stored at the front or rear of our deck as appropriate, depending on which method we call, but they're not going to actually remove those items. Inside of our peek method here, and I'm going to start with peek front, I need to make sure that there's actually something there for me to get first. So here I'm going to check to see if deck is empty, and I'm going to do that by writing an if statement that will call this dot is empty. If the deck is empty, I'm going to throw a new no such element exception to signify that. And I'm going to specify a message of deck is empty as part of the exception. I need to make sure that I go and import the no such element exception class, so I'll use the quick fix here in Eclipse to handle that. Once I know that there's actually something inside of my deck, I can just go ahead, grab my front node, so I'm going to and then return that with its data specifically. So I'm going to return this dot front node dot get data, and that's going to return the value that's stored in my front node at the front of the deck. The process of peeking at the front and rear of our deck to see what's in those positions is pretty straightforward. For the front, we're going to check to see if our deck is empty first, and if so, we'll throw a no such element exception. Assuming that there are things in our deck, we're just going to go and return the value from the front node. Things are pretty much the same when we want to go and peek at what's in the rear of the deck. We'll, again, make sure that our deck has items in it, and if not, we'll go and throw a no such element exception. Here, we'll go and return the value from the rear node, taking advantage of our rear node field that allows us to go directly there. Peek rear is pretty much going to be the same thing. We'll start off checking to see if the deck is empty. So I'm going to say if this dot is empty, then I'm going to go and throw a new no such element exception with the message that the deck is empty. Assuming that the deck is not empty, I'm going to go ahead and return what I get from going to this dot rear node and calling the get data method on that. The process of removing things from our deck is going to depend on how many items are already in the deck and if we're removing from the front or the rear. The simplest case is going to be if we're removing from a deck that has only one item. Here, the existing item is both the front and the rear. What we're going to do is we're going to store the value of the node that we're removing in a temporary variable. So you can see we've stored the value 33 in that temporary variable there. Once we've done that, we're going to go and set both the front and rear node fields to null. This will signify that there's nothing in the deck, and it's going to go and cut off access to the node that we're removing. Once we've done that, we want to go and decrement the size field, which will now show that there are 0 items in the deck. And then we just want to go and return the value from our removed node using that temporary variable. The steps involved in removing an item from a deck when there are already multiple things in the deck, which means we'll still have at least one thing left after the removal, is a little bit more complicated. Let's take a look at what we need to do if we're trying to remove from the front of the deck. We're going to start off by going and creating a temporary variable that'll store the value from the front node that we're going to be removing. Once we have that value safely stored in our temporary variable, we're going to start to cut that node from the existing front out of our chain. We'll begin by going and setting front node to point at the next node after the existing front. So you can see here now that front node is the second node in the chain, the value 55. Once we've done that, we're going to go and set that new front node, so 55's previous node, to be null, which means that we can't go backwards from that node. Once we've done that, we'll go ahead and decrement our size field, and we're going to go and return the value from our removed node. We don't need to specifically go and remove the link from our node that we're removing. It's next to the new front. We don't need to set that to null because that's just going to go away when we go and exit our remove front method. So when we go ahead and return that value, we're also getting rid of that front node and its link out. And that goes ahead and gives us a completed chain with our updated front and one fewer node storing values. Things are pretty similar when we go to remove from the rear of the deck. Again, we're going to store the value from the node that we're removing in a temporary variable. Here, we'll go and update the rear node field so that it points at the node that came before the existing rear node. So instead of the rear node being 92, it's going to become 55. Then we go ahead and update our new rear node's next field so that it's null. That's going to make it so that we have no way of getting to the node that we're removing. We're cutting it off from the chain. We'll go ahead and decrement our size field to reflect the updated count of how many nodes we have. And then we're going to go ahead and return the value from that removed node, and that will also go and get rid of the node when we return from our remove rear method. Let's go ahead into Eclipse and see how to code this up. So we have two methods here, one to remove from the front and one to remove from the rear. If we have a case where there's only one thing in our deck, it's not going to matter which of these two methods we call. They'll both have the appropriate code to go and handle that situation. Let's start off with our method to remove from the front. In here, the first thing that I'm going to do is go and create that temporary variable that'll have the value from the node we're removing. And I'm going to use the appropriate peak method for this here. So since I'm going and removing from the front, I'm going to call peak front. This will go and get me the value from that node that I'm going to be removing. It's also going to make sure that there was something in the deck to begin with. So if I have an empty deck, peak front will go and throw no such element exception. I don't have to handle that separately inside of this method. Once I have the value from the existing front safely stored, I'm going to go ahead and update my front node field to go and point at whatever is next after the existing front. So I'm going to say this.front node equals this.front node.get next node. If there is another node after the existing front, that new node is going to become the new front. If we only had one thing in our deck to begin with, get next node is going to return null, which will set front node to null, which is going to help signify that we have at this point an empty deck. Once we've updated front node, we want to go and look to see what its new value is to figure out what we need to do to go and finish cutting off access to that node that we're removing. I'm going to write an if statement here, and I'm going to say if this.front node is not null, then basically that means that there's still stuff in our deck. So I'm going to go to my new front node, this.front node, and I'm going to go and set its previous node to null. That way we won't be able to go backwards from the new front node. I'll go and put an else clause in here, and this is going to handle where the deck is empty. And in this case, since my deck is empty, I want to make sure that rear node is also set to null, because then both front node and rear node will be null because we don't have anything in the deck at all to be able to get to. Once we've gone and made those updates, we just need to do a little bit of bookkeeping. We're going to go ahead and decrement our size field. So we'll do this dot size minus minus, and then we're going to go and return the data that we removed from that node that we've eliminated. So we'll return removed data. Removing from the rear is going to be pretty much the mirror image of removing from the front. We're going to go ahead and start off by getting the data from the node being removed. So here I'm going to say var remove data equals this dot peak rear, which will either get us the value if there is a rear node, or if we have an empty deck, it'll go and throw our no such element exception. Next, I'm going to go ahead and update the rear node because I know that's definitely going to change. It's not going to be pointing at the existing rear node. We're going to say this dot rear node equals whatever comes before the existing rear node. So this dot rear node dot get previous node. And just like when we were going through and removing from the front, this is either going to go through and return the node that will be the new rear, so basically the second to last node in our chain, or if there was only one thing in our deck to begin with, this is going to go and return null. Once we've gone and updated rear node, we need to finish figuring out how to go in and remove the rest of the links to that node that is being removed. And we're going to do that by seeing if this dot rear node is now null. If it's not, then it means that there's still other stuff that's in our deck. So what I'm going to do is go to the new rear node, and I'm going to go and set its next node to be null. That'll finish going and isolating the node that we're removing. I'll go and include an else clause that'll go and handle where our deck is now empty. And in this case, we're going to go and set front node to null because we're not going to have any nodes left in the deck. Either way, we're still going to have to go and decrement our size. So we'll do this dot size minus minus, and then we're going to go and return the value that we removed. Let's go ahead and handle our size method next. And this one's just going to go and return the value of our size field. So we'll just say return this dot size. We're almost done with the process of implementing our linked deck class. Let's think about one of the last situations we might need to deal with, where we have to go and iterate over each of the nodes that's stored in our deck. We're going to be doing this when we implement the toArray method that goes and creates an array that contains the contents of the deck. In order to go and iterate over things, we're going to have to pick one end or the other of our deck, and then we're going to have to create a current node variable to go and point at the node that's at the end that we chose. I'm going to go and pick to start at the front, and we'll move forward through the deck, although depending on your circumstances, you possibly might also choose to start at the rear and go backwards. We're going to go forwards though. So I created this current node variable that's at my front node, and I'm just going to go in loop and keep on advancing current node by setting current node equals current node dot next node. Eventually I'll get to the point where current node becomes null, because after my last node, its next node is null, so when I go and update the value of current node, it's going to become null. When that happens, I've run out of nodes, so I can stop looping and I can finish up whatever I'm trying to do, whether it be going and returning a value or something else. Let's go ahead and code up our toArray method to export the contents of our deck as an array. This array is going to be sized just to have enough room for the number of elements that are actually stored in the deck, and we're defining based on the Java doc that the front of the deck will be placed in element 0. To get started, I'm going to go ahead and strip out the stub code that Eclipse generated, and we're going to go and create a new array. I'm going to say var export array equals a new object array of the same size as how many items we have stored in our deck. So I'm going to get that size from this dot size. Once I have that array created, I want to go and iterate over my chain of nodes to populate it. I'm going to need to create an integer variable that I'll call IDX. I'm going to initialize it to 0 to keep track of my position in the export array when I'm going and writing values to it. I'm also going to need to have a variable to keep track of what node I'm currently on. So I'm going to say here var current node equals this dot front node. And since I'm saying that the front node is going to be an element 0, that's why I'm going and starting at the front of my linked chain as opposed to, say, the rear. If for some reason I wanted to go and export things where we started off at the rear and had that be element 0, I could do that with our doubly linked nodes because I have the ability to go backwards. But we're just going to go forwards kind of the same way we've been doing things with our other implementations. I'm going to go ahead and create a while loop now, and we're going to keep on looping while current node is not null, which means that basically current node is still a real live node in our chain. Inside the while loop, I'm going to store the value of the current node in my export array. So I'm going to say export array sub IDX equals current node dot get data. So we'll get the value that's stored in our current node and place it in the array. And then I'm going to have to increment some stuff so that we move on to the next value. I'm going to increment my counter, so I'll do IDX plus plus. And then we're going to have current node go and move to the next node. So I'm going to say current node equals current node dot get next node. And that'll keep us moving down to the chain. And eventually, when we get to the last node that actually exists in the chain, its next node is going to be null, which will trigger us to fall out of this while loop. When we do get out of the while loop, the only thing that we have to do is just go and return our array. So we're going to return export array, and then that will go and give us the values that we had in our deck in an array. That's the last method that we need to go ahead and implement for our linked deck, so we've now got something that's ready for use. For this lecture's participation project, we're going to use a linked deck to go and store values. You'll need to download the participation project starter code that's posted in eCampus. This is separate from the starter code for the lecture itself. Once you've imported the project from the starter code into your Eclipse workspace, I want you to go ahead and create a new class that'll have a main method in it. Inside that main method, you should go ahead and create an instance of a linked deck using the class from the starter code. I want you to go and interact with that linked deck and treat it like it's a stack. So you're going to use the methods to go and add and remove things such that it works in last in, first out order. You'll need to store at least 5 values in the deck. It can be whatever type of data you want to use. It can be strings, integers, or something else. It's up to you. You'll need to go and remove and print those values one at a time once you've finished adding things to your deck. Since you're treating the deck like a stack, the items should be printed in last in, first out order. Whatever thing you added to the deck last should be the first thing that goes and prints out. When you're done coding up your project, you need to submit only the class that contains your main method. You don't need to turn in any of the other code. That's where we're going to end things right now for Deques. We still have more to come with looking at an array-based implementation of a deck. If you have any questions, please join the Q&A session or send me an email. Thanks, and have a great day.